Hey everyone, I'm Sam, and I'm here with Jiajia and Fangzhou, and we're here to present an ML-based fault injection method for autonomous vehicles. The safety and reliability of fully autonomous vehicles are the biggest concerns in the autonomous driving community. And as more articles and headlines get released about the various accidents that are happening around the world, the more concerned people are becoming of this developing technology. And that is why there's a need for a comprehensive assessment for autonomous vehicles and their safety. And one of the most popular and well-established methods for testing cyber-physical and computing systems is fault injection. However, autonomous vehicles pose a unique challenge for traditional fault injection methods. And this is because of the complexity of autonomous vehicles with the integration of software and hardware technologies. This, as well as the free-flowing operational environment with those variables to take into account. And as a result, the paper presents DriveFi, which is a fault injection framework for autonomous vehicles, which is able to identify hazardous situations which can lead to collisions and accidents. This system includes two parts: a fault injection engine, which is able to modify the software and hardware states of an autonomous driving system, as well as an ML-based fault selection engine, which they called the Bayesian fault injection, which is the part that is able to find the situations and faults that are most likely to lead to violations of safety conditions.
So this section provides an overview of an AI-driven Bayesian FI approach in the paper. So the figure illustrated the basic control architecture of an autonomous vehicle. It has some mechanical components and actuators that are controlled by an ADS system. And at every instance time t, the ADS system takes input from sensor I and takes inertia measurements M from the mechanical components such as velocity and acceleration. And it refers actuation commands A, such as throttle, brake, and steering angle. So the paper defines the instantaneous safety criteria of an autonomous vehicle in terms of X and Y direction. And the figure shows D-stop and shows the definition of D-stop, D-safe, and delta in X and Y direction for vehicle movement. And the D-stop means the stop distance that the vehicle will travel before coming to a complete stop with the maximum comfortable deceleration. And D-safe is the safety distance that an vehicle can travel without any collision. And delta is the safety potential. It is the D-safe subtracting D-stop. And autonomous vehicle is defined to be in a safe state when the delta is greater than 0 in both X and Y directions. So the goal of DriveFi is to test the ADSs in the precision of faults to identify any dangerous situations that can lead to accidents. So the faults injected into the architectural states of these processors can manifest as errors in the inputs, outputs, and any internal states of the ADS modules. And the DriveFi can directly inject errors into ADS outputs by computing the variables that stores ADS outputs. So the Bayesian fault injection is an ML-based FL that finds critical faults, which I mean the theta greater than 0 case. And the paper considers an ego vehicle moving in 2D spaces as shown in the figure. And the vehicle at time t has an instantaneous position in X and Y direction and speed v and handling theta, steering angle, v, and the L is the distance between the wheels of the vehicles. So the paper also assumes that the vehicle executes a special maneuvers that we can call an emergency stop to bring the vehicle to a complete stop. And this procedure is characterized by the equations of acceleration, and they are shown in the slide. So consider a situation which a fault is injected into the vehicle's ADS at time point K. We want to estimate the value of the stop at time K plus 1 when the corrected actuation commands of the previous time step have been acted. So the maximum likelihood estimate of velocity v under a fault is v at K plus 1. And the maximum likelihood values of x, y, theta, phi can be computed in the same way. And then the maximum likelihood of this stop can be computed using a procedure function p with the inputs of vx, y, theta, phi. And we also have an event x that is union of inertia m, actuation command a, row actuation command u, and an instantaneous state s. And we can use the expectation maximum algorithm to compute the mean and standard deviation of x. And in the last function, the d refers to a training data set that contains value of current, previous, and next event of x under normal operation and fault injectors.
So now we're going to discuss the actual ADS, or autonomous driving system architecture. And there are 5 layers to the ADS architecture. I'm going to briefly talk about each layer. So for the first layer at the bottom, we have the sensor abstraction layer, which does the pre-processing of the input data, noise filtering, gain control, tone mapping, demosaicing, and extraction of regions of interest depending on the sensor type. The autonomous driving system also supports the various sensors listed in the box below, where you can see the GPS, the radar, LiDAR, and cameras. Then we move on to the second layer, the perception layer, where its job is to identify environmental objects such as signs and other vehicles and pedestrians. And it's also its job for temporal tracking of objects and lanes to ensure that objects don't suddenly disappear from the frame due to misclassification or other errors regarding detection, so that the ADS is able to have both spatial and temporal redundancy. And for the localization layer, we are able to locate the vehicle in a world model using various sensor data, such as the GPS or camera/LiDAR. In this paper, however, they use camera/LiDAR in conjunction with maps. For the prediction layer, that is responsible for generating trajectories of the detected objects, where it can probabilistically identify objects in the path of the autonomous vehicle. And for the final layer, which is the planning and control layer, it uses all the data gathered from the previous layers and generates navigation plans, which are then used as a basis for the control signals that are sent to the vehicle, like acceleration, braking, and steering. There's also a surveillance system that ensures all modules are functioning properly, and it could trigger the Guardian module, which then chooses an action to be taken to prevent an accident. And so for the simulation hardware platforms, they use Carla and DriveSim. They're both Unreal Engine-based simulation platforms that are able to simulate a variety of scenarios, such as a complex urban freeway and weather conditions. And the ADSs of choice were NVIDIA's DriveAV and Apollo, which were put to the test in drive stem and Carla respectively, with some of the scenarios shown below. DS1 through DS3 were controlled by drive AV, and DS4 through 6 were done with Apollo and Carla. And with NVIDIA's drive AV, it was designed for the NVIDIA AGX Pegasus platform, which has 2 Xavier SoCs and 2 discrete GPUs. And with the Apollo ADS, they use the NUVA 6108GC, which consists of Intel Xeon processors and 2 NVIDIA Tiny XP GPUs.
And now we will talk about the Drive-Fi architecture. It contains the Unreal Engine, which is used to simulating the complex urban and freeway driving scenario. And then it also has the AI engine, that is to controlling the autonomous vehicle in simulation. And next, we also have the scenario manager, that is to coordinating the driving simulator and AI engine together. And it will also monitor the state of the software and the safety of the autonomous vehicle. So now we have the simulation tool set up. We also need additional modules for inserting faults. On the next page, we see there's a campaign manager. So by taking some configurations, the campaign manager generates a fault plan, and then it injects one or more transient faults into the ADS system. So next, we see there are 2 different modes for which the campaign manager can select. So one is the GPU fault injection. It basically injects faults into the GPU architecture state to reveal propagation of GPU fault to the ADS state. And the second mode is to inject source level fault to corrupt the internal state of the ADS software. And next, there are 2 different injection plans we will be using. So one is the random plan. Basically, it injects one or multiple faults randomly into the system. And the second one is to use the Bayesian fault injection approach we talked about previously. So with this setup, they were able to do the experiment. The experiment is shown as the following. They used 2 different control systems. One is the Drive AV and one is the Apollo. And 2 safety matrices are being used. One is the CIPO, which is the closest in-path obstacle, and the second one is the LK distance, that is the lateral distance from the center of the lane. So from the table, they conduct different campaigns. So the first set of campaigns is just by injecting single fault into the system. And the second campaign is to inject multiple faults into the system. And each campaign, it is targeting to specific modules in the system. In addition, they were also able to compute the baseline comparison or the golden runs. Basically, what they did is to simulate the tools without any fault injected into the system. And the results of their evaluation, for the source level fault injection, they conclude that the ADS platform was found to be robust to injection of a single fault. So here we show the graph of different safety matrix and run on different control platform. So we can see that in the, so if we compare the golden rounds with the 1 random rounds, there wasn't like too much differences between those 2 trials. And next, if we compare the golden rounds with the n random rounds, they conclude that there exists statistically different distribution between them. So it implies that the system were more vulnerable to the m random faults. And this is as expected because we are injecting more faults to the system. And next, another very interesting finding they have is that the ADS has the ability to compensate the faults being injected to the system. So on the image here, we're using the Drive-Fi to inject velocity to the system. And to compensate that effect, the ADS is adding brakes to the vehicle. So the graph on the right-hand side shows the accumulative brakes that was being added to the system. However, the ADS ability to compensate the effect of the errors is heavily dependent on the time and the location of the fault injected. And next, The method we talked so far, they can only create hazardous driving conditions when multiple faults has been injected. But we also need an efficient way to create hazardous driving conditions just by injecting one single fault. So they were using the Bayesian FI to efficiently inject single faults. And they're doing so by injecting faults where the ADS is at its most vulnerable state. The effectiveness of the Bayesian FI method is that 82% of the injected faults were resulted in the hazard state.
And so when describing the related work, they primarily talked about reasons for these previous methods to not be scalable. These two papers listed here were two of many examples of injection of invalid inputs or faults into an ADS to simulate with millions of miles on roads. But they described 4 reasons to why they were not scalable. Firstly, they lacked simulated or real data sets that were able to represent all kinds of driving scenarios. The second issue was that it would take billions of miles of driving to get any statistical measures. Thirdly, they were often restricted to DNNs and sensors. And lastly, even when they were able to find some bugs, the more rare and hazardous situations were exponentially more expensive, where faults would only manifest in certain conditions. So in conclusion, the paper presented a fault injection tool that was able to quickly find safety critical situations and was able to do so in a fraction of the time it took for random injection experiments. And such a framework could potentially be extended to other safety critical systems such as surgical or construction robots. And does anybody have any questions?